Hello everyone, my name is Jie from KAIST. Today I will talk about our work, which is scalable parallel flash firmware for many core architecture. Firstly, I will use a single slide to summarize this presentation. Nowadays, modern computer systems allocate many resources for the storage access. For example, multiple CPUs can simultaneously send requests to NVMe driver. The NVMe driver creates up to 64K queues, and each queue can create up to 64K entries to store the I/O request. The underlying NVMe SSD also can scale up its NAND flash resources. However, the SSD controller usually employs only a few cores. It exhibits poor performance, which can be the performance bottleneck. We can employ multiple cores in the SSD controllers to improve the performance. However, the existing SSD firmware cannot provide scalable performance. We propose DeepFlash, which is a scalable parallel flash firmware. It modulates the main functions of SSD firmware into different threads and fully utilizes the multiple flash cores to execute the thread in parallel. DeepFlash can achieve more than 1 million IOPS in real workloads. I will start the presentation with motivation. We are generating a large amount of data. By 2025, the total amount of data will increase to 175 zettabytes. To read the whole data within 1 year, the minimum storage bandwidth should be 1.2 multiplied by 10 to the 10 megabytes per second. If we use a hard disk as a storage media, we need at least 4 million servers as a storage node. This turns to the energy consumption to be 4.5 multiplied by the 10 to the 10 kilowatts per year. Instead, we can use SSD rather than the hard disk. We can reduce the number of servers to 1 million and reduce the energy consumption by 4 times. So to reduce the hardware cost and energy consumption, there is a high demand for high-performance storage to accelerate the read and write access. The performance improvement of storage devices is driven by multiple key technologies. For example, the hard disk has been replaced by NAND flash. The SATA interface has been replaced by the PCIe interface. The latest trend is adopting the NVMe protocol. It allocates many resources for parallel access. We expect the performance of NVMe SSD can exceed 1 million IOPS. However, the real performance of the existing NVMe SSD is still much far away from our expectation. Next, I will provide a scalable analysis to explain which factor actually impact the performance of NVMe SSD. Here is a baseline computer system. It includes the NVMe SSD. The NVMe SSD is attached to the PCIe root complex through the PCIe link. The NVMe SSD includes multiple flash arrays, which are connected to the flash channels. It also includes an SSD controller. The SSD controller includes multiple internal resources, such as PCIe modules, ECC engine, internal DRAM buffer. The SSD controller also includes a few cores for the computations. The cores are used to execute the flash firmware. Here I will simply explain the main task of the flash firmware. While the NVMe driver creates multiple submission queues and the completion queues in the host, the SSD controller allocates multiple doorbell registers. When the host submits a command to the NVMe SQ, the NVMe driver reads the doorbell registers in the SSD firmware. The SSD firmware will then fetch the commands from the NVMe submission queue. It will firstly place the command into the queues and pass the command to find out the address and the data length. SSD firmware will then check if the data already exists in the DRAM cache. If it's not available, SSD firmware will then translate the request logical address to a NAND flash physical address. The SSD firmware will generate the timing diagrams based on the request and leverage the flash physical address to access the underlying NAND flash. Once the SSD firmware completes the request, it sends the completion message to the NVMe completion queue and generates an interrupt. The NVMe driver will process the completion and read the doorbell register in the SSD controller. Each step of the SSD firmware is organized as functions. These functions are called by a single thread through event-based codes. We call such firmware as layered firmware. To increase the performance of NVMe SSD, we can integrate more flash packages to serve the requests in parallel. We examine the performance of flash array by varying the number of flash packages. As you can see from the figure, both read and write bandwidth can go beyond 1 million IOPS by employing 256 flash packages. We also measure the throughput of the whole NVMe SSD device. As you can see from the figure, the overall performance actually decreased to 180K IOPS. To figure out the root complex of the performance degradation, we analyze the SSD latency breakdown. As you can see from the figure, the flash access latency actually accounts for only 15% of the total SSD access latency when we increase the number of the packages to 256. The remaining 85% of the SSD latency actually comes from the SSD firmware. So SSD firmware will include the DMA, address translation, IO fetching, parsing, and caching. This is because the SSD controller has limited computation power to serve the increasing flash packages. To address the challenges, we can increase the number of cores in the SSD controller. Each core can execute an instance of the layered firmware. We examine the performance of the SSD controller by varying the number of flash cores. We expect the performance can scale with the number of flash cores. However, we measure the actual performance of SSD cores. Actually, the performance saturated at around only 500 kilo IOPS. This means the existing SSD firmware underutilizes the multiple flash cores. The root cause of such performance degradation is that many resources in the SSD firmware are shared by all the flash cores, such as the system memory space, SSD internal memory space, logical block address space, physical address space, and NAND flash access. These resources require lock protection to avoid conflicts from the different cores. Although we have many flash cores, the access to these resources should be serialized. This lock becomes the bottleneck to achieve scalable performance. To address the challenge, we propose DeepFlash. It is a scalable parallel flash firmware built from the ground. It can achieve a promising storage performance by increasing the thread level concurrency and minimizing the lock impact on shared resources. Our DeepFlash is also aimed to fully utilize the computation power of SSD controller, so we can minimize the number of flash cores. Our DeepFlash modulates the key functions of flash firmware as hardware threads. For examples, iLock threads manage the resource locking and unlocking. NVMQ threads interact with the NVMe driver and pass the commands. Cache threads manage the internal DRAM buffer. Trans threads translate the logical address of our request to the flash physical address. FCMD threads manage the flash transaction. We also add a BGC thread for garbage collection and a log thread for the metadata dumping. Our DeepFlash is flexible to scale the number of threads to fit the flash cores. We make the lock-free design for each thread to enable parallel executions among different cores. We also make a load balance designs to maximize the flash cores utilization. The IO request processing can be split into 3 stages. To get the stage include the NVMQ thread and the iLock thread. The trans-apply stage include the cache thread and the trans thread. The flash scatter stage include the FCMD thread, BGC thread, and the log threads. Compared to the layered firmware, DeepFlash is flexible to assign different set of threads to process multiple IO requests in parallel. Next, I will give more design details of each thread in the DeepFlash. Specifically, I will explain our lock-free designs to achieve high thread level parallelism and our load balance designs to improve the flash core utilization. I will firstly talk about the NVMQ thread. When the CPU cores submit a command to the NVMe submission queue, one NVMQ thread can fetch the command and pass the command. Based on the command information, it can generate a DMA to transfer the data from a non-continuous memory region in the host. However, when we employ multiple NVMQ threads, the NVMQ threads can fetch the same NVMe commands or access the data from the same memory location. All of these can generate conflicts. One possible solution for the lock-free is to statically assign NVMe submission queue and the completion queue to different NVMe threads. However, the different cores can generate different number of IO requests. So the different NVMe threads can experience unbalanced loads. To address this challenge, we propose a load balance design. Our main idea is to decouple the command function and the command parsing. We call it dynamic IO serialization. Specifically, we allocate local queues buffers in the storage side, which are identical to the NVMe submission queue and the completion queue. We also allocate two pointers, detail and dhead, for each queue buffers. The entries between the detail and the dhead store the commands which need to be processed. Next, I will show how these commands works. The NVMe submission queue and the completion queue are assigned to the NVMe0 threads. When the NVMe driver submits two commands in the NVMe submission queue, the NVMe0 thread will fetch the two commands and place them in the queue buffer. Unlike the prior schemes, both NVMe0 and NVMe1 threads can fetch and pass the commands from the queue buffer. To avoid the conflicts, NVMe atomically increase the dhead values with CPU intrinsics. In this design, NVMe threads can process IO requests from any submission queue, so that we can guarantee the load balance. Once the NVMe thread completes the IO processing, they fill the queue buffer with the NVMe completion queue. NVMe0 thread will submit the completion message to the NVMe completion queue. The NVMe driver will then process the request. Since the multiple NVMe threads can access commands from the same NVMe SQ, it can raise the consistent issues. For examples, let's suppose CPU submits request 1 and request 2, which can write and read the same page. We expect NVMe0 process the first write request and update the stale data in the NVFlash. Afterwards, NVMe1 will process the second request and read the data from the NVFlash. However, the NVMe0 can be stored. NVMe1 will access the stale data from the NVFlash. To address the challenge, we introduce iLock thread. In the same examples, NVMe0 gets the lock from the iLock threads. When NVMe1 processes request 2, it will firstly check the target data is either has been locked or not. NVMe1 has to wait until unlock the target pages. NVMe0 updates the new pages in the NAND flash and then release the lock to the iLock. NVMe1 then can access the new data from the NAND flash. SSD usually has billion pages. Tracking the lock of each flash pages can consume very high cost. Instead, our iLock thread organizes the lock information as a lock arbitrary. Each node records which address range has been locked and which NVMe queue owned the lock. As the NVMe queue thread can acquire the lock by sending the message to the iLock threads. If iLock responds with a failed message, the NVMe queue may retry and acquire the lock multiple times until it finally can get the lock. However, this can generate huge communication overheads. To address the challenge, we propose a lock optimization. Specifically, we propose a forward method. If one NVMe queue cannot get the lock, iLock can forward the message to the lock owner. The lock owner will process the corresponding request on behalf of the NVMe queue threads that do not own the lock. This design can reduce the communication overhead. NVMe queue threads communicate with cache thread to check if data exists in DRAM buffer. The cache thread maintains a direct map table. Each entry records the LP logical page number of the stored data and the corresponding location in the DRAM. However, the communication can be the overhead. In addition, as we only employ a few cache threads, it introduces centralized lookup overhead. We propose to expose the direct map table to NVMe queue so that NVMe queue can check if data exists in DRAM buffer. Cache thread only process cache miss and eviction. Here's examples to show how cache thread works. We build a direct map table. Each entry records a logical page number of the cache data. We say cache the logical page number. The data to be evicted, we say evict LPN. Let's assume page 0 is cached in the DRAM buffer. When write request comes, NVMQ cache check the request miss in the DRAM buffer. To serve the request, page 0x00 need to be evicted. So NVMQ revise the direct map table by moving the 0x00 to evicted LPN and record 0x03 into the cached LPN. NVMQ then forward the request to the cache threads. The second request wants to read the data from the page 0x00. NVMQ looks up the direct map table and finds out the page 0x00 will be evicted by the cache threads. To make sure the request 2 will read the latest data, NVMQ will send the request 2 to the cache threads. The third request wants to write data at page 0x06. NVMQ look up the direct map table and this data miss. Request 3 has to wait for the cache thread to evict page 0x00 and buffer the page 0x03. To reduce the waiting latencies, we directly bypass the request 3 to trans threads. Once the cache threads receive the request 1, it will evict page 0x00 to trans threads. Trans threads translate the logical address of our request to NAND flash physical address. However, the logical address space and the physical address space can be shared by multiple trans cores. They may translate the same logical address to different physical address. This will cause conflicts. We can use the lock-free designs in trans threads. To enable the parallel processing in trans threads, we can split the logical address space into chunks. The pages are spread to the different trans threads by modulating the address with the number of trans threads. Different trans threads also can map to different flash blocks in different flash channels. However, we observe that trans threads can experience unbalanced loads if the requests do not access the continuous pages. To address this challenge, we propose a new design by considering load balance. We can randomize the pages by XOR the least significant bits and the most significant bits. Next, I will move to the evaluation section. Our storage platforms use Xeon Phi as SSD controller. Although it provides 60 cores, we only use 12 cores in the evaluation. Our flash array contains 256 MLC flash packages, which can deliver more than 1 million IOPS bandwidth. We configure 4 different SSD platforms. 750 SSD and 4600 SSD are real SSD devices. Many layered is an SSD platform which creates multiple flash cores, and each flash core executes an instance of layered SSD firmware. DeepFlash is our proposed SSD platform, which includes all lock-free designs and the load balance designs. Firstly, I will show the overall performance. One of our observations is that the real SSD experience poor performance when serving the small IO request. Many layers achieve the better performance than the real SSD product. This is because the many layers employ more cores than the real SSD. DeepFlash can parallelize the IO processing in the SSD firmware, so DeepFlash can achieve best performance for small IO requests. We also compare the SSD controller utilization of DeepFlash and the many layers. As you can see from the figure, many layers has low core utilization because of local issues. In contrast, DeepFlash can utilize the most flash cores at the most time. We evaluate performance of the NVMQ threads by examining the static assignment approach and the dynamic IO serialization approach. The left figure shows that DIOS approach, which we explained before, can keep high performance with varying number of SQs. In addition, the right figure shows that with the DIOS, each NVMQ thread processes a similar amount of loads. This indicates DIOS can achieve high load balance. Next, we evaluate the performance of iLog. We set up 4 different iLog configurations. Page lock locks every page. I lock one megabyte locks every 1 megabyte data. I lock base and I lock forward locks every 256 kilobyte data. I lock forward enable the forward optimization. We firstly evaluate how much iLocks can impact the parallel execution of NVMQ threads. As you can see from the figure, iLock 1 megabyte achieves the worst performance. This is because locking a large amount of address range can block NVMQ threads. Page lock achieves the best performance. iLock forward can achieve similar performance as a page lock because it does not block NVMQ threads. Instead, direct forwarding the commands to the lock owners. We also evaluate the inquiry latency of iLock. Page lock has longest latency. This is because the lock RB trace is large. iLock forward can maintain a low inquiry latencies. Let me summarize this presentation. There is a high demand for high-performance SSD. However, the existing layered flash firmware cannot scale its performance with the flash cores. This becomes a performance bottleneck of SSD. We propose DeepFlash, which is a scalable parallel flash firmware for multi-core SSD controller. DeepFlash can fully utilize the multiple cores in the SSD controller and achieve high concurrencies. Our evaluation results show that DeepFlash can serve more than 1 million AUX for the real workloads. Thank you for your attendance.